In this video, we show how to do a simulation-based approach for analyzing paired data that is used in our Introduction to Statistical Investigations curriculum. Imagine you're at the plate in a baseball game and have hit a hard line drive. You want to try to stretch your hit from a single to a double. Does the path that you take to round first base make much of a difference? For example, is it better to take a narrow angle or a wide angle route? This was a question that W.F. Woodward tried to answer in his 1970 master's thesis. In his study, he used a stopwatch to time 22 different runners going from a spot 35 feet past home plate to a spot 15 feet before second base. Each runner used both methods with a rest in between. Therefore, this is a paired design. Woodward, of course, used random assignment to decide which path each runner would do first. It is important to note, as we will see, this paired design controls for runner-to-runner variability. Here are the times for the first 10 runners on both the narrow angle and the wide angle routes. And here are the dot plots for the times for all 22 runners running both routes. Notice there's a lot of overlap in these two distributions. The narrow angle mean is 5.534 seconds and the wide angle mean is a bit faster at 5.459 seconds. Also notice that their standard deviations are around 0.26 and 0.27 seconds. If we were testing these as independent samples, it would be difficult to detect a difference between the two methods when there's so much natural variation in running times. However, these data are clearly paired and should not be treated as independent samples. Instead, we will focus our analysis on the difference in times for each runner between the two methods. Our paired response variable will be the narrow angle time minus the wide angle time. Here are the differences in times for the first 10 runners and a dot plot of the differences for all 22 runners. The mean difference in running times is 0.075 seconds with a standard deviation of 0.0883 seconds. Notice that the standard deviation of differences, the 0.0883 seconds, is much smaller than the original standard deviations of the running times. This stems from the fact that although there is considerable runner-to-runner variability, the runners are fairly consistent how much time they take, typically between 0.05 and 0.2 seconds longer with the narrow-angled path, with a few of them taking a shorter amount of time. You can see this in the dot plot of the difference in times. You should also be able to see that these differences give us more convincing evidence that the narrow path takes longer than when we looked at the previous dot plots of the original data. In this set of dot plots taken off our applet shows the original data, not the differences, but each observation is paired with lines between the two base running strategies. What do you notice? Well, what you should notice is that the faster runners with the narrow angle tend to be the faster runners with the wide angle, and the same holds true for the slower runners. You should also see that most of the connecting lines slant from left to right, indicating a tendency for longer times with a narrow angle. This leaning would be impossible to pick up if we treated these as unrelated dot plots. So now we can ask whether this mean difference of 0.075 seconds is significantly different from 0. We define a parameter of interest to be mu sub d, the long-run mean difference in running times for runners using the narrow angle instead of the wide angle path. So here are our hypotheses. The null is that the long-run mean difference in running times is 0. And the alternative is that the long-run mean difference in running times is not 0. Notice we're using a two-sided alternative. Our statistic of 0.075 seconds is above 0, but we need to ask ourselves the same question we've asked before. How likely is it that we would see such a large average difference in running times by chance alone, even if the base running strategy had no genuine effect on running times? How can we use simulation-based methods to find an approximate p-value? The null basically says that the running path doesn't matter. This means that two times for each runners were going to be the same two times regardless of which strategy was being used. For each person, any difference in times was just by chance alone. So it doesn't matter which one we call the wide angle time and which one we call the narrow angle time. The two times are completely interchangeable. So we can use our same data set and for each runner randomly decide which time goes with the narrow path and which time goes with the wide path, and then compute the differences. Notice we don't break our pairs here. After we do this for each runner, then we'll compute the mean difference. We'll then repeat this process many times to develop a null distribution. To decide which times will be swapped, we're going to use a coin flip. Here we do this for the first 10 runners. If it's heads, we'll swap the times. And if it's tails, we won't. Notice if the times are swapped, the difference in times just changes sign from positive to negative, or vice versa. So here we continue to flip the coins for the first 10 runners. Now imagine these same coin flips being done for the next 12 runners. Depending on the coin flip, some of the dots move and some stay in the same place. With this first randomization, we get a simulated mean difference of 0.016 seconds, and this becomes a dot in our null distribution. In class, I would have my students flip coins and each get a simulated mean difference. The results from a class of 26 students might look something like this. Notice with this group of 26 students, we did not get anything as extreme as our observed mean difference of 0.075 seconds. So it appears that our observed difference is quite unlikely to occur just by chance. Let's repeat this process many more times using our match pairs applet. Pressing randomize, the applet simulates flipping a coin for each of the runners just like we did earlier. If the coin lands heads, we swap that runner's wide angle time with the narrow angle time. If tails, no change is made. After this randomization, our simulated mean difference is a negative 0.007, and this dot has been put in the null distribution. Now let's repeat this process 999 more times for a total of 1,000 repetitions. We see that our actual mean difference of 0.075 seconds only is way out in the tail, and only 1 out of the 1,000 repetitions were beyond 0.075 or a negative 0.075. Therefore, our p-value is 0.001. With a p-value of 0.001, we have very strong evidence against the null hypothesis and can conclude that the running path does matter, with the wide angle path being faster on average in the long run. We can draw cause and effect conclusions since the researcher used random assignment of the two base running methods for each runner. There was not a lot of information on how these 22 runners were selected to help us decide if we can generalize to some larger population. Let's review what we've done using our 3S strategy. We first computed the statistic in the sample. In this case, the statistic we looked at was the observed mean difference in running times. We then identified a chance model that reflects the null hypothesis. To do this, we tossed a coin for each runner, and if it landed heads, we swapped the two running times for that runner. If the coin landed tails, we did not swap the times. We then computed the mean of these 22 differences. Finally, we repeated this process 1,000 times, recording the simulated mean difference in running times each time, and thus obtaining a distribution of mean differences that could have happened if the null hypothesis was true. We found that the mean difference turned out to be at least as extreme as the observed difference of 0.075 seconds in just one of our 1,000 repetitions. This gave us a p-value of 0.001, which provided very strong evidence to say that the times for the narrow path and the wide path are different on average in the long run.